seems like it should be something very simple. Now I have to tell the computer, hey, that button that I just put on the screen, I'm still talking about that button. I want to look at that one, right? You then have to do a scope, right? This again, 6 lines of code has a function in it, which is creating a scope, and things are weird in this sort of world. Things that you define there don't escape, but if you talked about them above there, they're ambiguously escaping. You have the notion of readable assignment. That's where programming errors are the result of readable assignment. You have closures, something that still most career programmers don't understand correctly. You have asynchrony, which is probably unquestionably the hardest problem in programming at this point. You have objects and properties and the DOM. That 6 lines of code contains the context of years of work, right? You have to have spent years to understand what all of those things are doing. Yeah, sure, somebody might be able to Stack Overflow, copy some of this out and say, oh, I have a button that works. But that means they can't change it because they don't understand it, right? Those 6 lines of code, I joke here, like too long didn't read for 6 lines. But that is kind of the reality, right? Programming is hard. The question is, does it have to be hard, right? Is this sort of intrinsic? My standpoint is no. But this is what we ended up with Light Table, right? We've taken this kind of language. We took JavaScript, we took Clojure, we took Python. We're like, well, if we remove the feedback loop, programming will be easy now, right? Because you don't have to put the computer in your head. But this didn't change. All of this is still true, right? All of this is still necessary. And so the result of that, it didn't make things much better. And that's sort of like fundamental problem with trying to make it more accessible, right? It's programming, it's still programming, no matter how good of a tool you make for it. And the problem with that is that these languages and these tools were built around the idea that we're going to build applications, right? That the end result of programming is a little icon that you double click on your screen, it does one thing, and somebody writes it, and they give it to you, and that's that. But the reality is what we really want, when I started to think more about what it meant to make programming more accessible, we thought about making applications. I mean, we struggled with this for a long time. Right? We're like, oh, we're going to be building websites. We'll make it easy to build websites, right? But it's actually to do something far more fundamental, right? It's just to think. Because fundamentally, if you go back to the beginning of 1960s when a lot of what is modern computing came to be, the idea back then wasn't these single-purpose appliances, right? The idea was a tool to think with. And if we're going to make programming more accessible, ultimately what we're trying to do is make a thinking tool, not necessarily a tool for building large-scale applications, right? Because at the end of the day, the computer is the greatest thinking tool ever developed, right? If I know the mathematical incantation, this is punch holes in this card, I can get the computer to think for me, right? And that is a hugely, hugely powerful thing. When we went around pitching this to folks, we labeled it a superpower, because that is fundamentally what it is. It's one of the only times that given a computer, you can start with nothing else and create something of immense value, right? Just by knowing how to punch these holes. And so that's what sort of ultimately led us to this project that we're working on now. And that project's name is Eve. And then this idea, okay, I started with Visual Studio trying to make programmers better. Realized that the tools are actually not all the problem, right? So like the model of programming itself is a problem. Not Light Table, like, hey, the feedback is now out there, so that makes it observable, but it wasn't quite the way there. And it was still a tool, like we're still approaching this from a tools perspective. Eve is, what would happen if we tried to solve this problem from the ground up, right? Ignoring basically everything that exists. What would you build if you could basically imagine building programming today, right? So the first approach to this, of course, as a programmer, was to take all the things we thought were good about programming, we put them all in a pretty little package, and that's just going to work. So the first prototype of this was a thing that I showed at Strange Loop, which is a software conference. No, it's not playing. There it goes. It was a software conference that sort of like deals with a lot of the more interesting sort of avant-garde ways of thinking about the world. And so the idea was, okay, we'll take functional programming and immutable data, and we will put it in something that looks a lot like a Jupyter notebook, right? And we'll make it so that we're like literally working with the data, right? I right-click on a thing, I tell it what I want to do with it, and you can see all the results. And don't get hung up because it doesn't look super great at this point. I built this prototype in like 4 days, but it was really interesting because it took a problem that would normally take quite a long time, the better part of a day, for example. So this was taking a bunch of data out of Mongo, doing some usage data out of Mongo, and then doing some math on it, and then getting the graph out of it, right? And all this again was done by just sort of like dragging and dropping and like clicking on some things. And there are a bunch of interesting ideas in this. One is the idea that you're always kind of working with the domain itself. So you'll see here in a second, when I want to write out some math, I actually do it in math. By that I mean mathematical notation. Zoom ahead here because I'm apparently being slow. Right, so I want to sum over all x's and divide it by the number and I have average, yay. So the idea was, like, if you're working in a domain, let's say, for example, I had my drone example again, right? If I'm working with a drone, there's a drone on the screen, right? Instead of describing a set of operations that I'm performing, I just move the drone around, right? And it's capturing what those steps were. And then I can parameterize them by data or like get a chart or whatever I'm trying to do, right? So this is interesting. And we took a much better, much prettier, cleaned up version of this. We're like, this is awesome. We can build all sorts of things with it. Later in the video, I show like building a website this way, where you just have these tree of functions that do stuff. And it was interesting and cool as a programmer. It was very exciting. And I happened to be at the opening of Brett Victor's laboratory, CDG in San Francisco. And there were all of these non-programmers, brilliant people, physicists and mathematicians and all these people there, done on a program. And we set, like I said, a much better version of this in front of them and like, try it. Right? We're like, really excited. We're stoked. We're done. This is going to be amazing. And actually, the reactions were really positive. People liked it. They thought it was really interesting. They got why they would want to use it. And then, much to our horror, we watched them not be able to do anything in it, right? And I'll never forget the reactions we got, which is they were trying so hard, right? And they were very well-meaning. They genuinely wanted this to work, so they were willing to do things that most people probably would not really be willing to do. But there was this thing that surprised me, this thing that they started with. Out of all the things that I expected to find out in this, the hardest thing for the non-programmers to work with was scope. So in functional programming, you have these deeply nested set of functions, right? Everything's about this magical tree of functions that you're going to call. And the reactions that we got were really obviously bad. So like, somebody would look at it and go, they had some data at the top of the function stack, and they had some calculation they wanted to do at the bottom of the stack, right? And they're like, I want this down here. And you're like, kind of look at it and you go, well, you can't, you have to pass that through all of these, and you can't really do that. And they're like, I don't understand. I see it, it's right there. Why can't I use it here, right? Well, okay, fine. If I can't do that? Can I use this up there? No, you can't really do that either. We'd have to thread it through going back up, right? But like it's really, I no longer believed the arguments I was making, because we were trying to understand, like, the scope is really important, right? Like, you need it for functions are really important, and I don't know, that's like something we can't do, right? And so we tried to do a bunch of things. We tried to make this nicer. We're like, okay, well, we'll make it look prettier. And we tried to do a bunch of things to make the scoping thing less of an issue. So there's no variable shadowing. We did a much simpler version of scope. We do arrows. We colored things the same. We tried to do all of these different things. Nothing worked. It seemed like it was kind of like just this fundamental problem that was really hard to get over. And so that led us down this very odd line of questioning, which is, well, if our first attempt at this, what the industry seems to think the future of programming is like I said, functional and immutable, and yay. If that's not right, and scope is a kind of a problem which basically encompasses all of programming, where do we go from here, right? Like, what does it mean to remove scope from programming? So if you think about it, we have scope, can't have functions, so that's already scary to begin with. It also is that when you're building up these like nested data structures that you have, they're creating scopes, right? You're starting to worry a lot about where something is in this tree of data, and you don't want to duplicate because you put that data somewhere and you put it in another place, then they're going to be out of sync and you have all these problems. So it's another version of the scoping problem. So you can't have functions, you can't really have data structures. If you have data structures, you don't have anything that can keep things in order anymore. So you don't have ordering. So if you think about what programming is, if you ask a career programmer what programming is, they would probably say an ordered set of steps, typically executing functions over a set of data. All of that falls away if you remove scoping. And so we started to look into, well, has anything ever worked this way, right? And there is at least one massively successful example that works exactly like this. And that is Excel. Right, so Excel has a single data structure, but you don't work with the data structure directly. It has no scoping. If I can see a value, I can use it anywhere. It has no inherent ordering. It has scalar functions, but you're not really nesting these deeply, right? You're writing out basically the equivalent of mathematical formula, and it never goes deeper than that. So it has all these properties, and that is a fantastic result, and also a terrible result. But a fantastic result first. It's a fantastic result because 800 million people use Excel every single day. It is unquestionably the most accessible thinking tool available to us. And people have done amazing, truly amazing things with Excel. I was telling the story at lunch that I had this opportunity to talk to some folks at a Fortune 500 company, right? It's a cruise line. And they had this spreadsheet that was 10 gigs in size. They've been built up over a decade. No professional programmer had ever touched this spreadsheet, but it modeled the entirety of the Fortune 500 company's business. They could have moved every other system and run it off of this spreadsheet. Like, this is amazing, like totally, utterly amazing. And so that's great. But at the same time, Excel, this is the downside. Excel wasn't meant to do that kind of thing, right? So you have a joke around and like, yeah, if we made any changes to the spreadsheet, we had to go to lunch. Because it took an hour and a half for it to propagate, right? And Excel is constrained, right? It's a two-dimensional grid of numbers. If your problem is not easily specified as a two-dimensional grid of numbers, kind of out of luck. So we looked a little bit more. And we found that there was one other case that worked this way. Again, massively successful. And that is relational databases. Relational databases have the same set of properties, right? They don't, if you can see a value, you can use it anywhere. If you can see a table, you can use it, barring access rules, basically. There's no inherent ordering, either to the code, the execution, any of it, right? Even the data has no inherent ordering. You order it as you will. And again, no deeply nested functions or any of this crazy scope stuff going on. You just have basically functions and scalar values. And that was a great result, again. Certainly not accessible like Excel, but it solves the other side of the equation. It is a flexible thing, right? The world runs on relational databases. At the end of the day, basically every bit of data ends up in one of them. And we have built games and websites, all the things you couldn't imagine really building in Excel. So we discovered this, that, hey, relational databases is an interesting case. Let's see what people have been saying about them recently, right? There's got to be stuff other than Postgres out there that we can look into. And that's where we ended up on research out of here, actually. Jen Eierstein's lab, the Boom Lab, had been working on a language called Boom. And they were working on that language to do distributed systems. The idea behind it was that it was a query language, so a little bit like SQL, but it was based on Datalog. If you know what Prolog is, it's kind of like Prolog's little cousin. It does a lot less and is a lot simpler and is able to be a lot faster as a result. And they were building distributed systems, so they had Boom implemented to Hadoop, right? And well, that's really amazing because it was orders of magnitude smaller and all these great things. Could we build a website this way, right? Like, could we take this, maybe stretch it a little bit, think about it in a slightly different way, and how far could we take it? So I got this prototype. It was ultimately actually the prototype we raised money on. And it's a very interesting thing because if you read what these little things do, we have an intuition, which is that Prolog, right, or Datalog, or any of these, is written in predicate logic. And predicate logic is pretty hard to get your head around. But if you think about it, it kind of looks like fill-in-the-blank sentences, like those Mad Lib books we had when we were kids, right? It's like, put a color here. And if you squint and you think of it that way, if you think of these predicates that way, and you think of horn clauses as like, when you see this thing, do this thing, you get this kind of a natural way of thinking about it. So this is incremental, right? That was the button I was talking about before. So like, well, when I'm setting defaults, remember that the counter is 0. And when the counter has a value, draw this button. And when that button is clicked, change the counter as whatever its current value is to the current, to the value plus 1, right? And so like I said, we built, interesting things out of it. We always build QMBC because that's what everyone builds. But started building interesting things out of it. And we started to realize this crazy way of programming, that has no data structures, has no inherent ordering. When I built this prototype, originally didn't even have aggregation, which is interesting. Sort of made us realize that a lot of the things we think are fundamentally necessary for programming just aren't. You don't need them at all, actually. And so that's an interesting example. Because not only we built this website, you could say, oh, well, that's a toy or whatever. The IDE that it was written in it. And I know a thing or two about building IDEs at this point. I've built a few. Visual Studio is 55 million lines of code. Lightroom, which was far less than Visual Studio and was designed specifically to be as small as humanly possible, was over 10,000 lines of code. This was 600. We're talking about a totally different way of thinking about the world. Not only was it 600 lines, it was written in a week in a language that had no tools, that didn't even have aggregation, that had bugs in it, and we still managed to write this in a week. And so that is a tremendously awesome result. That, we can take some of the things that Joe's group had learned about distributed systems and apply them more generally to these other places. And just squint at this, it starts to kind of look like one of the holy grails of programming. Right? It kind of starts to look like an executable, an English executable specification, right? I read it to you, and if you think about the description you would give of the incrementer button, it's not very far from this, except maybe the when setting defaults part of it, right? And that's obviously pretty surprising and like really interesting. Right? Again, this is one of those things we've wanted for forever. Then we found out that actually this way of programming isn't that great. The whole, a lot of people still think that the English specification is like the future of programming. If we ever get there, we've made it and we're kind of done. And I don't really believe that's true. The reason why, after having programmed this way for a little while, is that if you read an English specification, every line of that English requires you having understood and internalized every previous line that was written. When we think about a don't need to know about this. I can just like go with this. And the specifications require you to basically understand the whole thing all the time. And you're on the shorter, so maybe you could reasonably do that. But when we actually tested this out with people, they were like, I can read these programs. I get what they're doing. But no one was successful in writing one, right? Which is kind of interesting. And yeah, maybe it was like tooling, maybe it was strategy, maybe it was whatever. But I think it's probably actually more fundamental than that. Like I said, I think it has to do with this context problem. That every line requires the context of all the previous lines. And so again, okay, let's check.
小川町ですね。やっぱりあんな遠い。こんな登ったかな。
Operations in these tables, and you could do it very visually, you could do it almost essentially just mouse-driven, right? And it could look like Excel. We sort of ran into a bunch of roadblocks here. Like I said, just like a very simple example of this is not knowing where anything came from. But as you started building up these more complex tables, you realize that people don't really think of their data this way. They have to think about keys a lot, right? And like joining on the keys, and it was still pretty hard. It wasn't the right solution. And it was shortly after this one, they were like, well, guys, I don't know yet about how to do the whole, like, make this thing accessible, but can we at least prove that it's a good idea, right, that the foundation of this is a good idea? Because we essentially broken this problem up into several problems. The first was, can we find a version of programming that was very simple, right? And by that I mean a few parts. And that version of programming has to be something that I could use, as well as it's going to work on Excel-like problems too, right? So it had to be a general-purpose language, but it needed to be very simple. And so we really liked the stuff out of the Boom Lab, and we had built some interesting things, but we wanted to deal with it more. We wanted to really try and develop some stuff with it and see what happened. And so we built this prototype, which, given how much time do I have? Not too much time. I'll show you very, very briefly what this looked like. So we have this thing, don't worry about what this looks like. So here's a clock, right? So we can zoom in a little bit. And everything in this language, like I said, it's just a kind of SQL, basically. It's kind of this weird way of thinking about the world. But all we're doing is query. And specifically, actually, we're building views in our case, which are queries that are always up to date, more or less. And so the first thing sticks a row in a timer table, which generates a timer for me. And that's what runs this clock. And then down here, we have this line which pulls in from the time table, which is what that timer sticks values into. And then we aggregate over that time table to get the latest time, and then we just turn it into hours, minutes, and seconds. Right? And then we draw a clock, and this is just me being bad at math. And then we have this little language down here that allows you to describe UI. Right? And we never, what's interesting about this language, you never describe So everything you saw being rendered on the right-hand side, all those tables, all the UI, even, so this thing is actually pushing processes distributed. So like it would run your program in another thread, and then subscribe to that other thread and pull data in. This entire little thing here was written in 200 lines. This is all of it right here. So again, this is like totally like crazy way of thinking about the world, but it kind of works, right? And so it's from this prototype that we sort of realized, okay, we don't yet know where we're going to present this to people, but this seems like a pretty sound model to build off of, right? There are definitely problems that we have to figure out. You know, there's performance and interesting things there. Although surprisingly, if you reduce your language to only operations on a B tree, which is what a query language ends up doing, it ends up being pretty fast, kind of by default. But there's still lots of interesting work to do there. But the foundation is solid. The foundation is the kinds of things we want to express, and we just have to figure out how to show it. Oops. Let me get back to my presentation. So we tried again. This time, I don't know why, but we ended up going back to the Excel thing. But this time we had something a little bit more interesting, which was you could actually build UI, and this was the first time that you had like a drag and drop UI builder. I know it's a little hard to see, but I dragged out a button there, right? And we're going to build the incrementer example, and I'm going to give my button a name, we'll call it incrementer, and instead of button down here that says get the clicks for that button, which is just a table. Everything is always just a table, right? If data's going to come from the outside world, it gets shoved into a table. If we want to do something to the outside world, we shove it into a table, and something in that there kind of looks for it and does something with it. So every time I click, I got a row in this table, and then the incrementer button is just counting the number of rows in the table, right? And this had that Excel thing going on, so you wrote like an Excel formula in here, you said count them, and then you could just drag that column onto the button, and that was now bound, now it's sort of like data bounded to the button. And it was asking you what to bind it to, and bind it to the text, and an increment button. So what a problem that took a professional programmer easily 30 minutes to do, assuming they knew what they were doing, and if they don't, who knows how long, could take 30 seconds, right? Like we could be much better at this if we thought about the problem slightly differently. That one, again, suffered from the same problems I described before, which was that you lost all the context when you're building up these tables, and it didn't really fit the model very well. So we tried this other thing where, like, hey, the UI builder thing worked out pretty well. Let's clone Foursquare. Let's clone a production-ready website and see what that looks like. And we built this each time we build a new view to try and do this, trying to understand it. We tested people. This one was good enough to build a production-ready clone of Foursquare. It was a business doing it. It was really good bad. Although not because of the UI, that was really bad. that the way we wrote queries in this was really awkward. We tried to mix the two. So we had the tables, right, and then we had the information, basically the sources of all the information from the tables up at the top, and it kind of looked like a SQL-y looking language. It was just bad. It's hard to explain exactly what is so bad about it until you use it and you like fully realize exactly how bad it is. I don't have enough time to show it, and I don't want to be ashamed, so I'm going to skip that one. But it was still interesting. It was the first time we did not have to write any code to build a real website, right? Like you could do this purely without typing anything, more or less, which is interesting, again, but it still wasn't right. So the next step after this was what we originally released. So we're all open source, and this is what we pushed out when we open source. And it was based on the situation that, well, all of our attempts of writing queries not in a query language that a programmer would understand have kind of been crappy. But we had the situation that when we pass around queries to each other, we drew them on the board. And we drew them as what looked like entity relationship diagrams, if you know what those are, little bubbles with, lines between them. And we were able to draw them that way to explain them to each other. Could we make them work? And we hesitated going in this direction because we know lots of problems with this kind of visual programming. And we even built, the boxes and arrows version of this long, early in our process and realized this is not going to work. But this is a very different property because what you're describing is not a set of steps or a data flow. You're describing a shape. You're saying, I'm looking in the database for a shape. Right? And specifically, this is a bonus shape. It's known as a three-click query with friends, basically. A friend was a friend of a friend was a friend, right? This happens to be a notoriously difficult thing in databases to optimize for. And you notice it has this wonderful property. I asked for a triangle, so I represent it as a triangle. This is one of the first times that people seem to understand relatively complex queries without us having to explain much of anything to them. A very simple set of things, and they're like, oh, okay, triangle of friends, it's a triangle, right? And then, here's a slightly more complicated one where you're getting the departments, you're trying to find out what percentage of the total cost each department is. So there's a bunch of aggregations going on in here, and then you're dividing those to get the percentage. And this is really interesting, because like I said, it was the first time people could understand it. It didn't suffer from the same boring problems that visual data flow languages do, because your shapes never get that big, right? It's not like you're describing the entire flow of a program, which could be of infinite size, basically. These were only asking for some shape, and it looks roughly like this. And so it seemed to scale halfway decently. Big systems in it, though. And we learned that this focus on individual queries and results wasn't really the right thing. It sort of took you away from what you're actually caring about, which is the data. You're always asking a question but an answer back. And this focused a lot on the question and a lot less on the answer. And these units ended up creating these silos that you then still want to back and forth with. It was a lot like how you deal with, if you're building a program and you have a bunch of different files, right? And you're going back and forth because the functionality you want is across 4 or 5 different files. Well, we have the same problem in this, but exacerbated, where it's like only looking at one function at a time, right? Okay, so we zigzag, because that's what we did. And we tried, hey, let's just take the MATLAB thing, the fill in the blank sentence thing, let's put it in a notebook like the very first one. Let's focus a little bit more on the answer, and let's make it a little bit more visual, and let's see what happens. So look at this. And this was interesting because this one would allow you to actually talk to it. So we did this, I got it running on my phone, and phones have dictation on them now. And you can literally just tell it a query, right? And it would just give you an answer back. This is really interesting and cool. That's a compelling place to eventually be. But we found that, unlike in the Jupyter case, where you're kind of writing out the set of steps you got to an answer for, we're talking much more they're alive, right? They're changing. They're not captured in time. So we know that a notebook is a really bad solution to this problem because it implies that this, then this, then this, then this, which is not true in this world, right? So you might do something at the bottom that would totally change the first thing, and that didn't fit the model very well. And also, it still feels like programming. You're still kind of doing this joining stuff. You had to know the names of the things you were looking for, right? Not the names of Chris, but the names of the relations. He's friends with, or has a house, right? Which again is a hard thing because who knows what they are. If you didn't write them, you kind of have to. So you could build tools that help you navigate that. But you're talking about lots of them. It doesn't matter what tools you have, right? Okay. So we laid the foundation. We still haven't figured any of this UI stuff out. We tried. We built basically 30 versions of Eve at this point, right? And we were like, okay, we're clearly doing something wrong. What assumption are we starting from that's screwing us up? And I think the assumption was, and once we threw it out, it proved things like a bunch, was that we were still approaching this as if we were building a programming environment, right? And the idea wasn't really to make programming environments, right? The idea was to enable a thinking tool. And a thinking tool doesn't have to look like a programming environment, so stop, basically. And where we are now, and the thing that we decided to commit to, because it's tested extremely well, and we're extremely excited about, doesn't look like programming at all. Not even a little bit. So I'm going to show it to you. A little bit. So we have a box, and it's kind of like a search box. It's just a really fancy search box, more or less. So I'm in the system. If you look at Chris Granger, there's not a lot about me. Here, I'll make it a little bit bigger. It's not a lot about me, but it says, I'm an employee at Codaway. That's the company that we run. I have a salary of 20, which is way too high. Change that, I have a salary of 2. So it's actually kind of like a wiki, interestingly enough. If you know much about wikis, this is what's called a semantic wiki, with some changes to it to make it a lot more powerful than semantic wikis typically are. But the idea here is important. One of the things we found every time we focused on the Excels that were representing things was that people don't think of their data like tables a lot of the time, right? A lot of the data that we really want to put into a system for thinking, some of it is going to look like a table, you should be able to do that. But a lot of it doesn't. A lot of it's stuff like random stuff about Chris, and I'm just going to write random properties that I haven't known about him at the time, right? That I am at a salary of 2, and his height is really short, right? Right, and now to that data is just available there for me now, and I can still ask questions about it. So, what is Chris Granger's salary? Well, it's 2. What about his height? The thing that I just add. Hey, short. Right? So it has this very, very fluid way of working with information. What's interesting about it is, we're doing the problems with this navigation thing that I was talking about before. Like, you have to know the names of all these relations and all that stuff. Well, in this case, they're just links, right? Like, here are all the things that I'm related to, and it tells me down here that I'm related to another thing called engineering. And if I go to I see the engineering card, and here are all the engineers at Codaway. And that's interesting, and I can dive around in these, just like you could on Wikipedia, right? And that's actually a really interesting thing because, A, we know Wikipedia works. B, if if you could imagine a Wikipedia where all the data was available to you to ask much more complex questions, that's a pretty compelling idea. So, for example, we know that there are departments. And I can look and say, oh, there are 2 departments here. This is just sort of generated by the system, right? If I add a new card that says it is a department, it'll show up here. But let's do something interesting with it. Like, let's sum the salaries per department. So, if you think about what just happened there, this is important. There is no direct link between department and salary. Departments don't have salaries. Employees have salaries, right? But because of the way the data is structured, we can pretty figure that out for you. So you can say it in this very natural way, right? I don't need to say, well, first get all the employees, then look at the department, then group them by that, and then sum them. And actually, if you want to see, we can actually see exactly what it chose to do. I can pop it open and it says, oh, it actually just gave you the process I described. Gather departments, gather the employees related to those, look at their salary, group them and sum them. But instead, we just ask this very straightforward question, right? And you can see this is back in my data table here, and this is another important thing. It shows you exactly how it got that answer. So this is something that SQL will leave you in the depths with. When you start to do things like grouping, you start aggregating, all the aggregates are lost, right? All the things you aggregated over are gone. One of the things that's amazing about this way of working is that we know where every aspect of the information comes from. We have complete and total provenance information. And so we can show it to you. This is exactly how we calculated the number 16. Here are the people that went into it. Okay, so I said, I mean, that's cool. You can ask questions, get an answer. But this isn't programming yet. You need to be able to form into something interesting. That's when you get programming. That's when you get change and stuff. So the way we do that is just by adding a card. So you card these cards. And what we want to do is we want to say, this is like a placeholder. We're going to take the department for each department up there, right? And we're going to say something new about that department. So we're going to say, well, that department has a total cost. The total cost is equal to the sum that we have there. And you see, now we have the total cost down here. And nothing looks like it's changed, but if we go back to engineering, you now see there's a new value down here at the bottom of this card that says engineering has a total cost of 16. I can now compute that. So we can start to say, departments with their total cost. Right? It's just new information. And so this is like, that's what the wiki where you can ask a question and generate new information as a result of that. And that is enough to build anything. You can build compilers this way. You can build websites this way. You can do all sorts of crazy stuff. But what I think is the most compelling to build an application to do anything here. For the most part, you could just work in this, right? You could just sit here and continue to ask questions and set up these little rules to do very interesting things. So for example, let's go back to Chris. And let's make my salary crazy again. Just way too much money. Right? And if we go back to look at the total cost of departments. You know, it doesn't really matter how I write this for the most part. Total cost of departments. You see it's 34. And actually, you know what? Let's change this around and say that departments with a total cost greater than 20. Right? So so that's questions about that. Get all the departments overspending. Send their heads an email, right? And the interesting thing is all this stuff is live. So if I come down here and open another one and go back to Chris Granger, you see my engineering with a total cost of 34, that's because of this really high salary. But if I go and I change it back to 2, all goes away to 16, right? This is all live. I never describe how things change. As they change, just use over the data. And so I was going to show an example here that was funny. So there's the Apple, released an Apple keynote. They showed a thing that got a lot of people really excited. So they showed on the Apple TV, you can now talk to Siri and have it find you, the example the specific query they gave was episodes of Modern Family that contain Edward Norton, right? So you can do that. So you say episodes of Modern Family with Edward Norton. There you go. That happens to be the only one. We can also say, well, how about without Edward Norton? How about we count them? Right? This way of working allows you to just very, very easily, very fluidly just start to ask questions. And I think that the craziest realization for me in all of this has been, if you took a step back and stopped thinking about this as programming for a moment, right? We managed to come up with a thing that doesn't look like programming anymore. It's just actually and there's still lots of work to do here, right? I'm not saying we've done it. I have no idea really what, programming is going to look like in 10 years. But my hope is that, whatever programming does look like, that it looks nothing like the programming we have now, right? The programming we have now, like, the last thing I want is you guys who are trying to cure cancer, who are trying to understand the cosmos, or whatever you're doing, have to read like Unicode, or have to read kind of Android, or like these ridiculous things that have nothing to do with the amazing stuff you're trying to do. I don't want to work like that at all, right? Because at the end of the day, like I said, the real goal here is a thinking tool. And that is what we have to get back to. And again, it's not a thinking tool for just me, right? I want you to remove the cards. I don't want you to have to punch a hole anymore. And I want you to be able to think for yourself. So that's my spiel.
こっち降りたわ。似たようなもんだからいいけど、ただ降りてもうとこっち降りてしまった。